Alright, so let's get started. There's a few problems on the board, on the screen here. Go ahead and see if you can deduce what the missing angles are for all of these. What the missing angles are. You should be able to do these mentally. Okay. So I can start you off with one of them. And I'm also going to be throwing in some jargon, some vocab that we've been using that we haven't used maybe in a little bit, so just as a reminder. So for instance on here, we have to remember a few things, a few facts, and that would be on this one that how many degrees are in a straight line. So if I look at the straight line, how many degrees are in that line? 180, right? So if this is right here 50 degrees, and you know the whole thing equals 180, how much would this angle have to be? Just 130, right? So our goal is going to be to take these rules that we learned probably a while ago at this point, maybe not even this grade, right? But from before, and we're going to start using them to prove things, right? And in order to do that, we have to get a common language figured out. So while this looks like a simple, oh yeah, you subtract from 180 to get whatever the missing angle is, there's a lot going on in the background that we don't really talk about. Well, we haven't really talked about up to this point, right? So we would say, if I was going to write this whole thing out, I could say something like this. This angle, EAD, right, plus this angle, BAD. They add up to 180. And then I can use this structure because these are two angles, a pair of angles that add up to a straight line, also known as a linear pair. I can assign some variables, like we didn't know this was equal to 130, so I can call that x and just say this is x. And then I can look at this picture and say, this angle is angle 50, so I can call angle BAD 50. And it converts a geometry problem into an algebra problem. Now this is the main reason why you guys have algebra class before you take geometry, because a lot of the proving and solving of geometry comes from algebra. Not always. We're going to have some cases today where it's only algebra, other cases where it's not. Okay. So if you subtract 50 on both sides, obviously we get our answer of 130. Okay. So that's the idea here. It's just adding some more language so that when we start proving things later today, we have a way of writing things down and finding all the missing pieces. So let's take a look at figure B. What are all the missing angles here? All right, so we have, I can actually label them. I can call them X, Y, and Z. How about that? X, Y, and Z. What are all those missing angles? And why are they what we say they are? Let's have a reason behind it. So I'll give you a chance to take a look at it. Don't overthink it. So, angle X, what do you believe that is? 150, right, degrees? Same reason. We know these two pairs of angles that are on a straight line adds up to 180 degrees, so the pair of angles must add up to 180. So if this is a 30, 150 will make that 180. What about down here? Of course, we're looking at, on this one, we're using this line. What would Z equal? 150 because, right? Same thing. 30 and what, for the green line, 30 and what makes 180, so we get 150 there as well. Now, of course, this also reveals a truth about intersecting lines, is that this is something called vertical angles. So you see how these two angles are supplementary to 30, and they come out to be equal? It's kind of like a scissor. If you open a scissor, if you open a little bit, the teeth open a little bit. You move your hands a lot, the teeth open a lot. So the angle of which you open a scissor with your hands is the angle of which the actual blades open up, right? So it's kind of like a scissor. right? But it's the same on both ends, right? And of course, using that information, we know that angle Y should be equal to 30 as well. And we'll be proving this later today. There we go. Now, all these are done with numbers. Now, unfortunately, when we are proving something to be true, which is our goal for today, how to actually get the language of proving something, we're not going to be using numbers because when we do a problem with numbers, it just shows that it works for that one set of numbers. Because we do it with numbers, it doesn't prove it for any number, any fraction of a number, any decimal of a number. It just proves it for that one problem. So if I move forward down here, let's see here. Oh, those are just repeats. We're going to start getting into some more general information. So take a look at this right here. Just this top part. Where to go? And there we go. Just that top part right there. What do you notice and what do you see about these three different pictures? Now this is at the top of your page, I believe, right? Yeah. So you can mark on this and start writing on these as you need to take notes. So what jumps out you? Notice how these are just problems that we just did. It's just a linear pair. Each of these is just a linear pair. They start off with a straight line and a ray coming out of there. Like so. And then we have these dotted lines. Now, can anybody spot any patterns any patterns between all these? What's similar, what's different? Compare and contrast. Sometimes to figure out how to solve a problem, you first have to look at it and actually decide, well, what am I looking at? What information do I know? So looking at all these, what do they have in common? Feel free to shout out whatever you come up with here. What's in common? So I'm hearing dotted lines are 90-degree angles, right? And at first glance, that may not seem obvious, but sometimes just looking at the picture a little bit longer and having things come out makes sense. Where do the red lines fall as far as the green lines? Where do those seem to fall? In the middle. So these red lines are perpendicular bisectors. All these red lines are perpendicular bisectors. That's what we started the whole school year with, is perpendicular bisectors. Alright, so it looks like these two angles are congruent. Right here, this angle and this angle looks congruent. This angle and this angle looks congruent, so I'm going to use a double. Right here and right here. Right here and right here. Now, a little reminder that I'm using different markings here because I know this red line bisects this obtuse angle here, right? So I know those two are this big angle is cut in half, so these are congruent to each other. I use a different marking for this acute angle that's cut in half because these angles here are not equal to these angles here. So that's just how we mark these. On here I did an arc with a little tick mark. Here I did a single arc, double arc. So you can choose any method you want as far as how you mark it. You can use the tick marks, saying this is different from this, or you can use the double or triple arc marks just to set them apart. Question? Nope. So that's the important part as far as how you mark them. Okay? Now, how do we actually know, or how can we actually prove if this is going to be a really 90-degree angle or not. It could just look like it. How do you actually prove it? That's the next question. We're getting into proof. And when it comes to proving something, it's very important that we have a really good system for saying something is true or not. Currently, in modern times, you have a bunch of people that are all wrong, agreeing with each other that they're all right, and saying and believing that they're right. This is very dangerous. We can't function long term with people just all agreeing with each other on the same wrong thing. We have to have a system of proving something is true with facts and information that is accurate, right? With 180 degrees in a line, whether you believe those are 90-degree angles or not, we can all agree, well, yeah, 180 degrees make up a line. And there's ways of proving that, right? It's not some number that somebody made up. It's definitely a fact, right? So that's what we're kind of on our way towards, is coming up with systems to prove something true. Possibly one of the best, most important lessons you can take from mathematics and apply to your, what are we going to do this in the real world? Coming up with reasons to prove something true, so you're not just, listening to somebody else. It causes you to think. You have to think critically. It's easier just to say, I'm not going to think. Let me look at phone and ask the Twitter, what am I supposed to think about this? You believe how many people have something controversial and they'll say, I don't know what to think of this. Let me go to the internet to find out how am I supposed to feel. As opposed to think critically on your own and come up with your own information, right? That's way more important than having just fallen in the crowd. And unfortunately, it has become in modern times more like a following your favorite football team. So you could be like a diehard Angel fan and say, no, the Angels are the best team in the world, even if they're... Quiet. Okay. Raiders or whatever you want. It's a long day. So, but my point is that if you ask a baseball fan who's an Angel fan, listen please. If you ask a baseball fan that's an Angel fan and says, yeah, Angels are the best team ever because they're my favorite team, you can't convince them otherwise, even though all these facts point to something completely different, even though they're like not even making the playoffs type of thing. So, listen. So the point is that we can't fall into this, well, people agree, or I have my own way of thinking, that's my opinion, and somehow that's equal to actual fact. We can't have that, right? We have to have a system of established getting things correct from the very beginning. So that's what we're looking at, and what you're going to be tasked with on your homework are going to be a lot of diagrams like this that just say basically nothing. It's just going to be a picture, and we have to do all the work to figure out, well, what's true and what's not, using only actual real information, right? So as it says here, Diego made the conjecture. An angle formed between the angle bisectors, and these are angle bisectors, those are dotted lines, is always a right angle no matter what the angle between R and L is. So you saw up here 3 different examples. No matter where this green line was coming out, you can see if we bisected both sides, it came out to a right angle. And he's saying that's going to be true no matter what. But it's difficult to tell specifically what angles Diego's talking about in his conjecture. Label the diagram, rephrase Diego's conjecture more precisely using your labels. So when you have a big problem, we have to actually define the problem a little more carefully so that we're all talking about the same thing. So it's always a good idea if you have a blank diagram to go through and just label all the different points. And that if there's 2 sides of things, that everybody's labeling points the same way and agreeing on them as you go along, as opposed to just making it up and everybody makes up different points. And then, of course, when you go to talk about it, nobody's going to agree on anything because we're talking about the same thing but in different ways. And you might notice that a lot in discourse where you think like 2 people are arguing over something, you're like, you guys are talking about the same thing and actually agreeing, but you're arguing back and forth on it. So it's very important that we define things the same way so we can have a discussion about it, right? And it was already determined that these dotted lines are bisecting. So here's what we can do. Here's some little tidbits I'm going to give you along the way. So if this dotted line cut this angle in half, ABD, ray BC cut this angle in half, that means both of these are the same length, or same size, same measure, right? I don't know what that measure is. And this is what's different from the beginning problems, that these are the same. I don't know what they are, though. So I can just call them the same measure. I'll say they're both A. They're either both 60 and 60, both 65, 65, both 62.5, 62.5. I don't know. But if we're going to prove something's true for all the angles, right? There's 3 different kinds here. I can't use actual numbers. I have to prove it for all numbers. And by using variables instead of actual numbers, it can do that. Now, likewise, I'm going to do the same thing for this acute angle that's much smaller. If this ray BE bisects DBF, I know that these two are the same. I'll call them both B. Got it? So, and exactly what is it? We've labeled it, so we've got that part down. And then we need to rephrase Diego's conjecture. What is he saying here? Well, if these are the same and these are the same, mathematically, what is he saying? And we already kind of highlighted this earlier up here. You can write it out as such. He is saying that the measure, I'll just say angle CBE is equal to 90. That's basically what he's saying. It's a lot of wording on how this thing is created, but in the end, he's just saying CBE is equal to 90 degrees, right? And CBE is equal to, right here, this right angle has 2 smaller angles, right? A and B. So another thing he's saying is A plus B is equal to 90. That's what we're trying to prove. If we can get to do some processes and prove that that A plus B equals to 90, we'll have proved Diego's conjecture. But this is actually the most important and most difficult step of proving something, is coming up with the question. Starting from a blank diagram with no labels at all, and then looking at this like, okay, that's a right angle. All right, well, that right angle is made up of 2 angles, A and B. So if I add those, I get the 90 degree. Coming up with those small pieces of information is everything. All right? And as we started earlier, we can start solving this. And this is one way, just one particular way for this particular problem to prove it. And how to prove another problem that's somewhat different from this isn't going to be different. So one thing about geometry is it's kind of cool, it's creative, but at the same time, you can't just take the last problem and say, well, I did this on the last problem, let me do it again. If it doesn't make any sense, it doesn't work, right? So it's not an autopilot like, here's 20 problems, give me the same, 20 steps with the same 20 answers. It's very different when you start proving something. You have to look at every problem by itself and realize there's going to be differences. So if there's another problem that doesn't have a 90 degree angle, obviously we can't say, well, A plus B equals 90 because if there's no 90 degree angle. What we can do is use and build a bag of tricks, right? So we know from the first problem here, well, if I have a linear pair, those 2 angles add up to 180. That's not disputable. That's just plain geometry, no pun intended. All right, so the same thing exists here, but instead of having 2 angles, I have 4 angles. So what I can do instead is say, well, I don't know what A is, I don't know what B is, but I do know this one long straight line is equal to 180. And I know all 4 of these angles have to add up to that 180 degrees. So I can say something like this. If I add up all the angles, A plus B, and have it equal 180, right, that would be true. And whether you think it's 90 degrees or not, whatever side you're on, you could agree, well, yeah, we know that much. That's definitely true. Can't dispute that, right? This is how we actually prove something, is you go step by step with facts that are undisputable, between whatever side you're on, and don't proceed until you can agree what you just did is mathematically okay. And then we can start using a little bit of algebra. And here's where algebra comes in. Not a whole lot, but it's important. So if you have one A and another A, how many A's do you have altogether? 2 a's. So a plus a equals 2a. All right, remember this. And if we have this b and another b, how many b's? 2 b's. All right, and so that means 2a plus 2b equals 180. Now, did you guys do factoring last year in your algebra class? Okay, so factoring is like reverse distributive property. So a little sidebar here. If you have something like this, 2 times a plus b, what does that equal? Yeah, 2a plus 2b. That's what we just have right now. Okay, so that's called distributive property, right? You learned that a long time ago. The reverse direction is called factoring. You might not know that, but you probably know how to do this already. So if I have a polynomial and it has a common factor, like these both have a 2, I can factor the 2 out, and I end up with this. 2 times a plus b. It's just the reverse of distributive property. So if you want to think of factoring as undistributing, that's fine. It's like addition and subtraction. One puts it in this format, multiplying the 2 in. One, in effect, divides the 2 out. You're dividing every term by 2, and you're writing it in front. So that's called factoring. That. And this all came from just a blank diagram with no, labels, no nothing, right? But we were able to extrapolate all this stuff just from our background knowledge of algebra and what we know from our warm-ups and all that good stuff. Now, nice thing about geometry is that you already know what the answer is you're going towards at the very beginning. Since we formulated our answer from the very beginning, I already know my goal is to get a plus b equals 90. Now, can you tell me, do you see a step that goes from here to here? What can I do to change this algebraically so that I end up with this step right there? What's that? Close. If I multiply 2 times 2, I'll get 4. If I multiply 180 times 2, I'll get 360. But I want to get 90. So what can I do instead of multiplying? Come on, I know you know it. All right, so I have a plus b here. I have a plus b here. So a plus b is totally fine. I got what I want. My goal is to get 90 on the right-hand side. Now, how do you suppose I take two numbers, 180 and 2, and get an answer of 90? Yeah, you divide, right? So if I divide both sides by 2, it actually gets me to my goal. Because 2 divided by 2 is 1. Right? So I have a plus b. Technically times 1, but we don't write the 1. And then 180 divided by 2, which is 90. And you can see that was my goal, to show that a plus b equals 90. And that's what I ended up with, a plus b equals 90. So now we know for sure a plus b equals 90. But I never used numbers. So you know what that means? It works for any numbers in the whole wide world. Every fraction, every decimal, every integer, as long as they're positive, of course. I just proved it for an infinite number of problems using algebra. And that's the importance of doing this, as opposed to, let me just put in numbers and see if it works for that particular problem. Right? And there's many, many ways of solving this. This is just one, and it's algebraic. But this is where we're leaning towards, is finding something between algebra and geometry on any given problem, or sometimes just geometry. We just did a bunch of reflections and rotations. We can use those to prove as well. Okay? We'll be going over that. But it kind of makes sense that a plus b, like this part right here, equals 90 degrees. That means this a and this b also add up to 90 degrees, which they have to, because if this a plus b is 90, these two, a and b, have to be 90 to make 180 degrees. So we could make an argument that this a and this b add up to 90 degrees every single time as well. In order to make the 180 happen every time, that must be true. So there's a lot of patterns in here that we're going to be diving into. Just don't be afraid to be creative. And what we just did here It's going to take some practice because the problems kind of change. They're slightly different, and we can't go on autopilot. That's what's going to be different. We really have to look at each problem one by one. So lots of good explanations, lots of good reasons for why something's true. And if you're trying to prove someone that didn't believe it's true at first, this type of argument would definitely say, well, they wouldn't have anything to rebuttal against and say, well, no, that can't be right. It's like, well, yeah, that step's right, that step's right. You can do that to both sides. So I guess that must be right, and I have to accept it because nothing seems out of line. So that's another part of when you're debating, is that when you hear something, you're like, I don't believe you, and they give you evidence that's undisputable, you have to be willing to say, okay, you're right. There's nothing wrong with that. Any step of your argument, there's no flaws with it. So what I was saying was wrong, and what you're saying is right. And you have to be okay with that, and not stick to something because, nope, Angels are my best team ever. Nope, no matter what. Well, the Dodgers won 106 games. The Angels won like 60. Doesn't matter, right? We can't just make things up and say, well, I believe it, right? And we can't fall into the fallacy of, well, there's two opinions, therefore they're equal opinions. That's not true either. You can have someone that's completely wrong, have a bad opinion, someone has a very informed opinion. They're not equal to each other. They're not 50-50, right? The more informed, the more strong your argument is. Because there's some people who say, well, we'll just agree to disagree, and, oh, we're both equally right, both equally wrong. No, you're not. Not usually. There are some definite right, or I say right, I'd say strong and weak arguments. Let's put it that way. Okay, so what you guys are going to do right now is do basically the same thing, but you're going to prove vertical angles are actually congruent and have an argument for it with some mathematics. Notice how there's no 90-degree angles here. So you can't just say, well, last problem we did this, so I'm going to do that here. There's no 90-degree angles. You have to use it as a, an example, but not as a template. Just to blatantly not think and then just repeat. All right, so very similar. We already know it's true, right? And I already kind of, on the second warm-up problem, we already talked about it a little bit. But this is just with numbers, 30 degrees. How do I do that without the numbers, with A's and B's and things like that? That's what you're trying to do here. Okay? So give that a shot. Follow the directions. Do exactly what we did on the first one. Start by labeling it. And you guys should be working on this with each other in your group. It's not something you just say quietly and then go do it by myself. So give it a try. See how it goes. And I'll just be coming around and checking the progress and seeing what we do. In the interest of time, let's look at this together right now. So walking around, I had about half and half. But the first step we can all agree on. Just like we did on the first problem, we have to label these so we're actually talking about the same point. So it doesn't matter how you label it. It doesn't need to be like mine. But you need some sort of system to talk about everything. All right? Otherwise, we can't get specific enough to solve anything. And then someone said, like, well, A's and B's, right? So they put, well, this is an A, and I know vertical angles are congruent, so that must be, this is A as well. So you can see how this is similar but different, right? Same thing here. I can call this B, I can call this B. So between these problems, you're going to have similarities, A's and B's maybe, but just you notice how it's not the same. You can't just cookie cutter it, template it. Now, we don't have any 90-degree angles here, but we do have a couple of 180s. We have two lines, right? So I have this one, and I can write this out. And here's where it's kind of a different type of problem. We have to be careful. And I can use, I'm trying to prove B and B equal together, A and A are equal to each other. So I'm going to use the actual angles instead. I'm going to say I had two groups that came up with this. BEC. Instead of saying angle B, I'm just saying BEC. Plus DEC. Alright. We know adds up to 180. Right? Non-disputable. And we also know, well, if it's true for one line, it must be true for the other. Okay? So I can come up with two of these angles, A and B, right? And I can say AED and once again DEC also equal 180 degrees. So two straight lines, two linear pairs, two equations. So that's the two groups that got this fully developed. This is what they came up with. Is this something you didn't know? Did you know that both straight lines add up to 180 degrees? Yes. So this isn't about if you know it or not. It's trying to figure out the language. This is like the commas and apostrophes and things like that of mathematics that we just have to learn to write with it. And it gets easier the more you practice. Like, where does apostrophe go? You know, is it a colon, semicolon? Stuff like that. It just takes practice. And you have to have faith moving forward that you know how to do this. It's just how to write it down is a little different when you're trying to prove something's true for all infinite number of combinations of numbers. Right? It takes a little more rigor. Now, here's a truthism with mathematics and equations. So if these are true right here, like 180 is equal to 180, right? And I know angle DEC is equal to angle DEC. So what else must be true? Yeah, these two are equal to each other, right? And that is how I'm proving the angles are congruent. Those are the two angle B's. I just proved these two angle B's are equal to each other. So this actually shows how those vertical angles are the same because they're both supplementary to the same angle A. Both supplementary to angle A. This B is, and so is this. In short, that I could subtract, if I had numbers here, if I say this is 150, actually no. If I said this was 30 right here, I can do this line and subtract and get this to be 150, but then I could use the other line, subtract B, and I can get 150. Thus, I get the same angle on both of these. That's how I know they're congruent. They're supplementary to the same single angle, which is exactly what we did up here. Right? This is 30 degrees. We found out each of these is 150. It's just how you write it down when you're proving something. It takes a little bit more when you're trying to prove it for all possible values, right? Now, this is actually called the transitive property, the fact that this is equal, therefore these must be equal. So, but we're not going to worry about that, but that proves that vertical angles are congruent. I did it by labeling it and just using the only thing I could work with, and that's, I had straight lines, so I had to use the fact that they're equal to 180, and that's just about it. Alright, so I'm going to pass out an assignment right now.